The James Webb Space Telescope cost $10 billion and took 30 years to build. When it finally opened its golden eye on the universe in 2022, astronomers had a clear expectation of what they would find. They expected to see the early universe the way you would expect to find the nursery of a newborn: dark, quiet, and filled only with the simplest raw materials. Wisps of hydrogen gas slowly gathering under the gentle pull of gravity. The first dim sparks of stars just beginning to ignite. That is not what they found. Within the first months of data, something was deeply wrong. The telescope was staring back in time to when the universe was only a few 100 million years old, a blink by cosmic standards. And sitting there, in that era of supposed emptiness, were galaxies. Not small, primitive, barely formed galaxies. Massive, fully structured, star-crammed cities of light. Galaxies comparable in size and mass to our own Milky Way, sitting in a time period when the physics we understand says they cannot possibly exist. To understand why this is not just surprising but genuinely destabilizing, you need to understand what it actually takes to build a galaxy. Gravity is not fast. It takes an extraordinary amount of time to pull diffuse gas into clumps, compress those clumps into stars, let those stars live and die across generations, and slowly accumulate enough mass and structure to call something a galaxy. The theoretical minimum for building something as large as the Milky Way was previously estimated at well over 1 billion years, but the telescope was finding galaxies of that scale at just 290 million years after the Big Bang. That is not a small discrepancy. That is like finding a fully grown 200-year-old oak tree in a forest that was planted last Tuesday. The galaxy that became the symbol of this crisis has the designation JADES GS-Z14. The Z14 portion of that name is the key. It is the redshift number, and it tells us that we are seeing this object not as it is now, but as it was when the universe was barely 290 million years old. Redshift works because the universe is expanding. As light travels across billions of light years, the stretching of space stretches the wavelength of that light, pushing it toward the red end of the spectrum. The more redshifted, the more ancient the source. A Z14 redshift puts this galaxy so deep in the past that it should not be a galaxy at all. It should be a cloud. But the chemical evidence is what truly breaks the model. When the telescope analyzed the light from JADES GS-Z14, it found carbon. It found oxygen. This sounds unremarkable until you remember that the Big Bang created essentially two elements, hydrogen and helium. That is the complete inventory of the early universe. Carbon, oxygen, iron, and every other heavy element in existence had to be manufactured inside the cores of stars through nuclear fusion, and then scattered across space when those stars exploded as supernovae at the end of their lives. This is a multi-generational process. You need stars to form, burn for millions of years, die violently, scatter their ash, and then allow that ash to be gathered into new stars and planets. Finding carbon and oxygen in a galaxy at 290 million years old means that entire generations of stars had already been born, lived, and died before this galaxy even appears in our telescope. The timeline simply does not accommodate this. It is the astronomical equivalent of walking into a house that was supposedly built yesterday and finding century-old antiques inside. The antiques prove something happened before the house existed, and that proof is deeply unsettling. For 50 years, the dominant story of early cosmic history rested on a period called the Cosmic Dark Ages. The theory was that after the Big Bang, the universe spent roughly 400 million years in a state of pitch blackness. Gravity was slowly, painfully pulling hydrogen gas together. No stars had yet ignited. No light existed. The universe was a cold, dark fog gradually organizing itself toward the first dawn. It was a tidy, logical theory. It matched the mathematics of known physics. It gave cosmologists a comfortable timeline to work with. James Webb has made that theory extremely difficult to defend. If massive, fully formed galaxies exist at 290 million years post-Big Bang, then the dark ages were either much shorter than we believed or were not dark at all. The universe did not slowly blink awake over hundreds of millions of years. Something was building structure, generating starlight, and cooking heavy elements at a rate our standard cosmological model cannot explain. The lights were already on when we thought the universe was still in bed. This created a crisis that split the physics community into roughly 3 camps, each with a different explanation for what the telescope is showing us. The first camp says the universe is simply older than we think. The second says the universe operates in cycles, and we are seeing inherited relics from a previous cosmos. The third says our fundamental model of how the universe expands and evolves is wrong in ways we have yet to fully understand. Each of these explanations carries consequences so large they would rewrite physics textbooks. Physicist Rajendra Gupta proposed what may be the most radical version of the first explanation. He argued that the universe is not 13.8 billion years old. He suggested it might be closer to 26 billion years old. The reasoning behind this is that our method of measuring cosmic distance and age relies on the redshift of light. Gupta draws on an older, controversial idea called tired light, which proposes that light loses energy as it travels across vast distances, causing it to appear more redshifted than it actually is. If this effect is real, we have been systematically misreading the cosmic clock. The universe would be twice as old as currently accepted, and that extra time would be more than enough for gravity to build the galaxies James Webb is finding. The problem is that accepting this solution requires dismantling almost everything else we know about dark energy, the expansion rate of the universe, and the precision measurements of the cosmic microwave background that underpin modern cosmology. It does not so much solve the problem as trade it for 5 different problems, and the physics community has not embraced it. But neither has it been fully ruled out, which tells you something about how seriously the telescope's data has shaken the foundations. The second explanation comes from a Nobel Prize-winning physicist named Roger Penrose, and it is conceptually the most disorienting of the 3. Penrose does not believe the Big Bang was the origin of everything. He believes it was a transition point. His model, known as conformal cyclic cosmology, proposes that our universe is just one chapter in an eternal sequence of universes. Each universe expands for trillions of years, eventually reaches a state of maximum entropy, and then undergoes a geometric transformation that triggers a new Big Bang. The end of one cosmic cycle and the beginning of the next are mathematically equivalent events, even though they feel astronomically different. In this framework, the massive early galaxies James Webb is finding are not impossible. They are inheritance. They are the surviving debris, the gravitational echo and accumulated mass of the universe that existed before our own. The atoms in those galaxies have already been through one complete cosmic cycle. They did not form in 290 million years. They formed in the trillions of years of the previous universe and simply carried their history across the transition. Penrose does not ask you to take this on faith. He points to what he calls Hawking points. When a supermassive black hole finally evaporates through a process called Hawking radiation, a process that takes longer than the current age of our universe by many orders of magnitude, it releases a final burst of energy. Penrose argues that these bursts from the previous universe left permanent marks on the fabric of reality, subtle circular patterns in the cosmic microwave background radiation. James Webb is now scanning for these patterns with greater precision than any telescope before it. If the Hawking points are confirmed, it would mean we are living inside a universe that bears the scars of one that died before us. We would not be the first generation. We would be inheritors of a very old house. The observable universe, the region of space from which light has had time to reach us since the Big Bang, forms a bubble roughly 93 billion light-years in diameter. That number alone is staggering, but here is what makes it claustrophobic rather than expansive. The edge of that bubble is not a fixed wall we could eventually reach. It is a moving boundary defined by the speed of light and the expansion rate of space. And because space itself is stretching, galaxies near the edge of our observable region are moving away from us faster than the speed of light. Not because they are physically moving through space faster than light, but because the space between us and them is expanding. The light from those galaxies will never reach us. They are, for all cosmological purposes, gone. Every second, galaxies cross that horizon and vanish from our observable universe permanently. We are not exploring an ocean. We are watching the shoreline shrink. James Webb was built to peer right to the edge of this shrinking shoreline. And what the telescope is finding, there is not the clean boundary of an isolated universe. It is finding hints that our bubble may be interacting with something on the other side of it. Something we cannot directly observe, but whose gravitational influence is reaching through the wall. This leads to one of the most disturbing anomalies in modern cosmology, the dark flow. A team of astronomers mapped the motion of hundreds of enormous galaxy clusters. In a universe that is expanding uniformly in all directions, these clusters should show no coordinated movement. They should drift randomly, like debris scattered in all directions after an explosion. But they do not drift randomly. They are all moving. And they are all moving in the same direction, toward a specific patch of sky, at a speed of roughly 2 million miles per hour. The mass we can account for inside our observable universe is nowhere near sufficient to generate that much gravitational pull. The math requires something outside our visible horizon, something of extraordinary mass, pulling at these clusters like a magnet through the wall of a room. The best candidate is either a massive concentration of matter left over from some primordial fluctuation, another universe entirely running parallel to ours, or a region of the multiverse so dense that its gravity bleeds across the boundary between cosmological bubbles. James Webb is refining the dark flow measurements, and the signal is not going away. If anything, the data is making it clearer. Something enormous is out there in the dark, and we have no way to look directly at it. We may not need to. There is a mark already on our sky that some physicists believe is the signature of a collision with another universe. It is called the cold spot. When we map the cosmic microwave background, the faint afterglow of radiation left over from the early universe, it is nearly uniform in temperature everywhere. Nearly. There is one region in the southern sky, roughly 1 billion light-years wide, that is measurably colder than everything around it. For years, this was written off as statistical noise or instrumental error. But James Webb has confirmed that the cold spot corresponds to an actual structure, a supervoid, a region of space where the density of matter is dramatically lower than the surrounding universe. A void can be colder than average simply because photons lose energy climbing out of gravitational wells. But this supervoid is colder than a void of its size should be. The discrepancy points towards something more violent. Physicist Laura Mersini-Houghton, working within the framework of multiverse theory, proposed that the cold spot is a bruise. If our universe is one bubble in a larger multiverse, and if two of these bubbles collided early in their histories, the impact would have pushed matter away from the collision point and left a cold, sparse scar. The geometry of the cold spot matches this prediction with uncomfortable precision. If this interpretation is correct, we are not isolated. We are floating in a crowded foam of other universes, and we have already taken one hit. The question physicists quietly ask is not whether there was a collision, but whether there will be another one, and whether the next collision will be a glancing blow or something that ends the story entirely. While the universe is pulling our galaxy at cosmic scales toward unseen attractors, the situation inside our galactic neighborhood is no less disorienting. Data from the cosmic microwave background shows that our entire galaxy, along with the several dozen galaxies that make up the local group, is moving at a speed of approximately 630 kilometers per second. That is over 1,400,000 miles per hour. We are not drifting. We are being pushed and pulled simultaneously by gravitational forces on a scale that dwarfs anything in our immediate neighborhood. For decades, the dominant explanation pointed toward a structure called the Great Attractor, a gravitational anomaly roughly 150 million light-years away that was assumed to be the source of this motion. The problem is that the Great Attractor was never massive enough to fully account for our velocity. The numbers kept coming up short. It was only in 2017 that astronomers looked carefully at what sits behind us, in the direction we are moving away from, and found the answer to the other half of the equation. There is a massive region of near-total emptiness directly behind our local group. They named it the dipole repeller, a void so underdense that it creates a kind of negative gravitational pressure, effectively pushing everything around it outward, the way a low-pressure system in the atmosphere draws wind toward it. We are not just being attracted towards something. We are simultaneously being repelled away from a void. We are caught between a gravitational vacuum and a gravitational magnet, moving through space at over 1 million miles per hour, with no way to stop, no way to steer, and no certainty about what waits at the end of the trajectory. For 60 years, humanity's primary strategy for finding intelligent life in the universe was to sit down and listen. We built radio telescopes, pointed them at promising stars, and waited for a signal. The SETI project, the search for extraterrestrial intelligence, operated under a fundamental assumption that if intelligent life exists, it will want to communicate, that it will be broadcasting in ways we can detect, the way we have been broadcasting since the first radio tower went up more than a century ago. We waited. We heard nothing, just the cold, flat hiss of background radiation and the occasional natural pulse of a pulsar or a quasar. James Webb changed the strategy. Instead of waiting for someone to call, the telescope became a hunter. The reasoning is elegant. You can turn off a radio transmitter. You can encrypt your data. You can make yourself electromagnetically silent, but if you are alive, you are breathing. Biology is a chemical fire. It consumes molecules and excretes waste, and that waste has to go somewhere. On Earth, life has completely transformed the atmosphere. We breathe in oxygen and breathe out carbon dioxide. Microbes cycle nitrogen. Plants produce oxygen. The entire chemical composition of our atmosphere is a fingerprint of biological activity. Take away the life, and the atmosphere would quickly settle into a dead, stable equilibrium of inert gases. James Webb is scanning the atmospheres of exoplanets using a technique called transmission spectroscopy. When a planet passes in front of its star, the starlight passes through the thin shell of the planet's atmosphere before continuing to James Webb-S mirrors. The gases in the atmosphere absorb specific wavelengths of light, leaving a distinctive pattern of dark lines in the spectrum, a barcode. By reading that barcode, the telescope can determine what gases are present in an atmosphere hundreds of light years away, without ever visiting the planet. It can detect water vapor, it can detect methane, it can detect oxygen, and crucially, it can detect chlorofluorocarbons, the synthetic gases produced by industrial processes. Nature does not make chlorofluorocarbons. Only factories do. If the telescope detects that barcode in a distant planetary atmosphere, there is only one explanation. Someone is down there making things. The results so far have been sobering. Planet after planet shows stable, dead atmospheres. Carbon dioxide and nitrogen sitting in perfect chemical equilibrium, just as they would be on a world with no biology. Earth's atmosphere is chaotic by comparison. We have oxygen and methane coexisting simultaneously, two gases that react violently with each other and should rapidly destroy one another. The only reason they persist is that life keeps replenishing them. Our atmosphere is in a constant state of chemical imbalance because something living is constantly stirring the pot. The atmospheres James Webb is scanning are not being stirred. They are at rest. And a resting atmosphere from a biological standpoint is a dead atmosphere. This is what scientists call the rare Earth hypothesis, and the James Webb data is providing it with uncomfortable support. We tend to assume that life is the natural end state of chemistry, that if you give a planet water and starlight and enough time, biology will emerge. But chemistry does not want to be alive. Chemistry wants to be in equilibrium. Life is a sustained violation of chemical equilibrium, maintained by continuous energy input, extraordinarily complex molecular machinery, and a staggering amount of luck. Consider what was required to make Earth habitable: a star stable enough not to strip the planet's atmosphere with violent flares. James Webb is finding that the most common type of star in the galaxy, the red dwarf, is a violent, flaring machine that would repeatedly sterilize any planet in its habitable zone. Earth needed a large moon to stabilize the axial tilt that determines our seasons. Without that stabilization, the poles and equator would trade places on chaotic timescales, making sustained life nearly impossible. Earth needed a massive outer planet, Jupiter, positioned to intercept a significant fraction of the asteroid and comet bombardment that would otherwise sterilize the inner solar system with catastrophic regularity. Every one of these conditions needs to be met simultaneously. The telescope is showing us solar system after solar system that is missing one or several of these requirements: violent stars, unstable orbits, dry planets. The safe, stable, improbably fortunate garden we inhabit may not be common. It may be extraordinarily rare, and if it is rare enough, it may have happened only once. If we are alone, the implications are crushing, not just emotionally, but in terms of responsibility. Every extinction-level threat we face, whether self-inflicted or cosmic, is not just a threat to a species. It is a threat to the only island of consciousness in the observable universe. If we fail, the lights go out everywhere. But let's assume the optimists are correct. Let's assume life is not rare. Let's assume the galaxy is populated with intelligent civilizations. Then the silence becomes even more disturbing. If the universe is full of minds, why is no one talking? The answer may be that talking is suicidal. Think about the history of contact between civilizations on Earth. When a technologically advanced civilization has encountered a less advanced one, the outcome for the weaker party has been almost universally catastrophic. Now scale that logic to interstellar distances, where there is no shared language, no possibility of negotiating before the encounter, no ability to verify the intentions of the other party. You receive a signal from a star 400 light-years away. By the time you receive a response to your reply, 800 years will have passed on Earth. There is no real-time dialogue possible. There is only the initial detection, the calculation of whether the detected civilization represents a threat, and the decision of what to do about it. This is sometimes called the dark forest theory, a term popularized by Chinese science fiction author Liu Cixin. The universe is a dark forest in which every civilization is an armed hunter. The hunters cannot communicate safely because there is no way to verify whether another hunter is friend or enemy across the void of light years. The logically safe move is always to eliminate the potential threat before it can eliminate you. And so the forest stays quiet. Every civilization that understands the game goes silent. Every civilization that does not goes extinct. If the dark forest theory is correct, humanity has made a catastrophic error. For the past 100 years, we have been broadcasting our location, our technological level, and the chemical signature of our biosphere with reckless enthusiasm. The I Love Lucy television broadcast from the 1950s has now expanded outward at the speed of light and washed over thousands of star systems. We sent the Voyager Golden Record with detailed information about our biology, our location in the galaxy, and our level of technology. We have beamed high-power directed signals at stars using the Arecibo dish. We have been screaming into the dark forest for a century, apparently unaware that the correct behavior is to freeze and be silent. Our continued survival to this point may not be evidence of safety. It may simply be evidence of insignificance. We are currently at a technological level where we are interesting enough to be noticed, but not yet threatening enough to justify the expenditure of resources required to sterilize us. We are at the level of an anthill. You do not pour gasoline on an anthill unless it is in your kitchen. The moment the anthill starts building a wall near your foundation, the calculus changes. We crossed an important threshold in the 20th century. We split the atom. We left our planet. We demonstrated the ability to develop exponentially. We went from biplanes to orbital rockets in less than 50 years. That trajectory is exactly what you would monitor if you were a cautious, ancient civilization trying to identify which species on which planets are approaching dangerous capability thresholds. The silence may not be peace. It may be the held breath of the forest before a decision is made. Here is the detail that makes this viscerally immediate rather than abstractly theoretical. You do not need a starship to sterilize a planet. You need a rock. A dense projectile, perhaps the size of a city bus, accelerated to 90% of the speed of light, carries kinetic energy equivalent to a significant nuclear arsenal. No warhead required. No ship needs to arrive. The projectile simply impacts, and the result is the rapid termination of complex life on the surface. Now consider the physics of detection. We see the universe through light. Information about events reaches us at the speed of light. A relativistic projectile, traveling at 90% of the speed of light, is only slightly behind the light it displaced when it was launched. Effectively, the warning and the weapon arrive at nearly the same moment. We would not watch it approach. We would not have time to evacuate or respond. A star would look perfectly peaceful, and then the atmosphere would catch fire. James Webb may right now be observing a star system from which such a projectile was launched 500 years ago. The telescope would see nothing wrong. The image it receives is 500 years old. The projectile, if it exists, is already most of the way here. We are not safe because we cannot see the threat. We cannot see the threat because it travels at the speed of our own vision. If the universe is a hostile place, then the physics of the universe itself is also hostile territory. We tend to treat the laws of physics the way we treat the laws of mathematics, as absolute, unchanging, bedrock truths that we can rely upon completely. But James Webb is generating data that suggests the laws of physics are not as stable as we assumed. There is a crisis in cosmology with the understated name of the Hubble tension. It refers to a mismatch in two independent measurements of how fast the universe is expanding. The first method starts with the earliest light we can observe, the cosmic microwave background radiation, a snapshot of the universe at just 380,000 years after the Big Bang. Using the physics embedded in that ancient light, cosmologists calculate that the universe should be expanding at a rate of approximately 67 kilometers per second per megaparsec. A megaparsec is roughly 3.26 million light years, just to give the number a physical reference. The second method measures the expansion rate directly, by studying the distances and recession velocities of galaxies and stars in our local neighborhood right now. This method uses standard candles, Cepheid variable stars whose luminosity cycles at predictable rates, and type Ia supernovae which all explode at roughly the same brightness. When you use these methods, the expansion rate comes out at approximately 73 kilometers per second per megaparsec. These two numbers should be identical. They are measuring the same universe. The fact that they are not, with a discrepancy of roughly 9%, means either our measurement tools are systematically flawed, or the universe is not behaving the way our models predict. Before James Webb launched, some cosmologists hoped the tension would dissolve when telescopes became precise enough to eliminate measurement errors. James Webb is the most precise telescope ever built. It has now confirmed the measurements made by its predecessors with even greater accuracy. The Hubble tension is not an error. It is a real feature of the universe, and we do not know what it means. The most alarming possibility is that something is changing. That the expansion rate itself is not constant. That some unknown energy component is accelerating the expansion in a way that our standard cosmological model, lambda CDM, does not account for. If the expansion is accelerating beyond what we expect, the long-term fate of the universe shifts from a cold, gradual dissipation into a violent ending called the Big Rip. In the Big Rip scenario, dark energy continues to accelerate the expansion until the repulsive force of expanding space overcomes every other force in the universe, one by one. First, galaxy clusters would be torn apart, then galaxies themselves, then solar systems, then planetary systems. In the final moments, the expansion overcomes the electromagnetic force binding atoms together. Matter ceases to exist. The atoms that make up your body would simply come apart, not explosively but silently, because the space between their components would grow faster than the forces holding them together could compensate. James Webb's data on the expansion rate suggests we may be accelerating more rapidly than expected. The gas pedal is being pressed harder than our current models account for. Whether this means we are heading toward a big rip, or simply that our models are incomplete, the telescope cannot yet say. But the direction of the data is uncomfortable. If the large-scale structure of spacetime is uncertain, the small-scale structure is equally disturbing. We treat empty space as the floor of reality, the lowest energy state, the absolute nothing below which there is nothing further. But quantum mechanics suggests that empty space is not actually empty. It is seething with virtual particles constantly popping into and out of existence, and it is pervaded by a field called the Higgs field, which gives mass to every particle in existence. The Higgs field has a value. That value determines the properties of matter, and the value of the Higgs field may not be at its lowest possible energy state. The masses of fundamental particles, particularly the top quark, which James Webb is helping to constrain through precision cosmological measurements, sit uncomfortably close to the boundary that separates a stable Higgs field from a metastable one. A metastable Higgs field is analogous to a ball resting in a shallow depression on a hillside. It is in a local minimum of energy, but not the global minimum. There is a deeper valley lower on the hill. The ball is stable for now, but it is not at the bottom. Given sufficient random fluctuation, or through a quantum tunneling event, the ball could spontaneously roll out of its shallow depression and fall into the true minimum. If the Higgs field drops to its true minimum energy, a bubble of true vacuum forms at the location of the transition. Inside that bubble, the laws of physics are different. Different masses for particles, different strengths for fundamental forces. Chemistry, as we know it, is impossible inside true vacuum. Atoms cannot form. The structures of biology dissolve. The transition propagates outward from the initial point in all directions at the speed of light. There is no warning. There is no defense. There is no detection ahead of time. You cannot run faster than light. The bubble front erases everything it encounters simultaneously with the arrival of any information about its approach. You would not see it. You would not feel it. The laws that allow your neurons to fire and your consciousness to exist would simply change, instantaneously and without any subjective experience of the transition. For all we know, such a bubble was triggered in the Andromeda Galaxy 2 million years ago. The Andromeda Galaxy is 2 million light-years away. If vacuum decay occurred there 2 million years ago, the bubble has been expanding for exactly long enough to be arriving at Earth approximately now. We cannot see it coming because the light that would carry information about its approach is moving at the same speed as the bubble itself. We would have no way of knowing, and we would have no time to care. If the ground might dissolve beneath us and the sky might be closing in around us, the question of what reality is actually made of becomes urgently relevant. James Webb is helping to probe this question by studying black holes at the centers of galaxies, and what the physics of black holes reveals about the nature of space itself is deeply destabilizing to our everyday intuition. When matter falls into a black hole, all the information encoded in that matter, every particle's position, velocity, spin, quantum state, is apparently preserved. This is not optional. Quantum mechanics has a rule called unitarity that states information cannot be created or destroyed. It must be conserved. So when a star falls into a black hole, all the information about that star has to go somewhere. The assumption would be that it goes inside the black hole, filling up its interior volume the way water fills a container. But Stephen Hawking and Jacob Bekenstein calculated something that violated this intuition. The amount of information a black hole can contain is proportional to its surface area, not its volume. Not the three-dimensional space inside the event horizon, but the two-dimensional surface of the event horizon itself. A black hole twice as massive has 4 times the surface area and can therefore hold 4 times the information, not 8 times. The volume did not matter, only the surface. This is the holographic principle, and its implications extend far beyond black holes. If the information content of any region of space depends on the area of its boundary rather than its volume, then the universe as a whole obeys the same rule. All the information contained in our observable universe may be encoded on the two-dimensional surface of the cosmic horizon, the distant boundary of our observable bubble. The three-dimensional reality we experience, every object, every person, every moment of apparent depth, would then be a projection. Like a hologram on a credit card that appears three-dimensional but is actually flat, we would be the three-dimensional projection of two-dimensional information stored at the edge of space. The version of you reading this would be a ghost, not metaphorically, literally, a high-resolution projection of data encoded on a surface billions of light years away. You feel solid because the projection is good. Your pain and pleasure and perception of depth are features of the rendering, not of some underlying physical reality. If we are projections, then the anomalies James Webb is finding take on a different character. The impossible galaxies existing too early. The Hubble tension suggesting the universe is expanding faster than it should. These would not be mysteries of an organic, physical universe struggling to explain its own history. They would be artifacts of computation, rendering errors, glitches in a simulation approaching the limits of its processing capacity. This framing is not as fringe as it might sound. Serious physicists, including Nobel laureates, take the simulation hypothesis seriously not as mysticism, but as a genuine theoretical possibility that follows from the mathematics of quantum mechanics and information theory. The resolution of reality, the minimum meaningful length scale below which distances have no meaning, is called the Planck length. It is approximately 1.6 times 10 to the negative 35 meters. You cannot subdivide space below this limit. It is the pixel of reality. And a universe with pixels is a universe with a resolution. And a universe with a resolution is a universe that is being calculated rather than simply existing. The speed of light would be the frame rate. The Planck constant would be the sampling frequency. Gravity would be the physics engine. And the reason you cannot exceed the speed of light, the reason quantum superpositions collapse when observed, the reason information cannot be destroyed, these would not be mysterious coincidences. They would be features of the operating system. If the universe is running out of processing power, we would expect to see glitches at the edges. In the deep past, where the simulation has not fully rendered, at the boundaries of our observable region, where the data density is lowest, and in extreme physical environments like the cores of black holes and the first moments after the Big Bang, where the simulation would be under maximum computational load. James Webb is looking directly into all of those environments, and it is finding anomalies in all of them. The entropy problem makes this even more acute. In information theory, entropy is not just disorder. It is the erasure of distinguishable states. When information becomes scrambled beyond reconstruction, it is gone. This is exactly what happens to us, physically and cognitively, over time. Every cell division introduces small errors into the DNA. Every memory access degrades the precision of the stored information. Every year, the pattern that is you becomes slightly less faithful to what it was. We call this aging, but in information theoretic terms, it is data rot. James Webb is showing us the endpoint of this process on a cosmic scale. It observes galaxies that have exhausted their gas supply and stopped forming stars. They are not exploding or collapsing. They are simply becoming quieter and more uniform. The complex patterns of stellar formation and interstellar chemistry that characterize active galaxies are settling into a lower-energy, less structured state. The universe is doing what the second law of thermodynamics says it must, moving toward maximum entropy, maximum disorder, minimum information content. Every ordered structure in the universe, from a star to a civilization to a moment of human consciousness, is a temporary deviation from this trend. We are not what the universe is trying to produce. We are what the universe is in the process of erasing. This brings us to a concept that is mathematically rigorous but psychologically devastating: the Poincaré recurrence theorem. It states that a finite, isolated system with bounded energy will, given enough time, return arbitrarily close to any previous state it has occupied. In other words, in an infinite future, any arrangement of atoms that has ever existed will occur again. The deck of cosmic cards will be shuffled infinitely many times, and any hand that has ever been dealt will eventually be dealt again. The number of years required for a Poincaré recurrence of a system, the size of our observable universe, is incomprehensibly large, something on the order of 10 to the power of 10 to the power of 100 years. Written out, the number would fill every book ever written with nothing but zeros. But if time is infinite, this number is not a barrier. It is just a delay. If recurrence is true, then you will be reconstructed. The specific arrangement of atoms that constitutes your brain, your memories, your personality will occur again and again. In a physics where consciousness is a physical pattern rather than a supernatural essence, the reconstructed pattern is not a copy. It is you. The interval of unconsciousness between your death and your recurrence is subjectively zero, because a pattern that is not active has no subjective experience of the passage of time. This is the eternal return, a concept the philosopher Friedrich Nietzsche used as a thought experiment to probe the weight of one's choices. He posed the question as a demon's whisper: this life, as you live it now, you will have to live it again, and innumerable times again, with nothing new in it. Every moment of joy and every moment of suffering, repeated without variation, forever. Nietzsche intended this as a challenge. Could you live in such a way that you would willingly relive your choices indefinitely? But physics makes it less of a philosophical thought experiment and more of a literal description of a possible reality. And the mathematics of statistical mechanics adds one more dimension of horror to this picture. The Boltzmann brain paradox points out that in a universe of random thermal fluctuations over infinite time, complex ordered structures can arise spontaneously from chaos. The question is, which is more likely to arise? A whole consistent universe with a coherent history, or just a single brain with false memories of a universe that never actually existed? The mathematics is not kind. A single brain containing memories and the subjective experience of a life is vastly simpler to assemble by random fluctuation than an entire universe with billions of years of consistent physical history. Statistically, for every real person living in a real, coherent universe, there should be an astronomically larger number of spontaneously fluctuating brains experiencing a simulated history that never happened. If you take the mathematics seriously, you have to sit with the uncomfortable probability that you are not a real person in a real universe. You are a momentary fluctuation, a statistical accident, hallucinating a coherent past that was never real. And in a fraction of a second, the fluctuation will end and you will dissolve back into the static. The universe, it turns out, does not need to be malevolent to be terrifying. It only needs to be indifferent. And yet, here is what the full picture reveals when you stop looking at the parts in isolation and look at the structure of the whole. Every one of these constraints, every limitation, every source of existential alarm is also doing something else. The same speed of light that prevents you from ever truly knowing the present state of another person also guarantees that cause and effect are always ordered. Without this limit, the universe would be a tangle of causality violations, where effects can precede their causes, and the coherent flow of events is impossible. You cannot have a consistent story without the limitation that information cannot travel faster than light. The same entropy that promises to erase everything you have ever loved is also the engine of time. Without a thermodynamic arrow pointing from low entropy to high entropy, without the irreversibility of physical processes, the universe would have no meaningful temporal direction. Events could run forward or backward with equal probability. There would be no persistent identities, no stable patterns, no possibility of history. The fact that entropy increases in one direction is what gives time its one-way nature and makes experience, memory, and causation possible at all. The fact that consciousness evolved in a universe that will ultimately destroy it is not evidence of the universe's hostility. It is evidence of the universe's complexity. A universe simple enough to be stable forever would be too simple to produce stars, planets, chemistry, and biology. The same processes that enable the emergence of life are the processes that eventually end it. You cannot have one without the other. We are a product of the complexity, and we are subject to its costs. Astronomers who study the James Webb data professionally spend their careers sitting with the scale of what the telescope is revealing. The scale of the universe as Webb now allows us to perceive it is not the comfortable cosmic backdrop we learned about in school. It is an arena of forces and processes and timescales so vast that human experience is not even a rounding error. The period of human civilization, from the first cities to the present day, occupies less than the last second of a year-long documentary about cosmic history. And yet, in a universe of burning gas and dead rock and frozen vacuum, we are the anomaly that knows it is anomalous. A galaxy containing 400 billion stars does not know it is a galaxy. It cannot wonder about its own size. It cannot feel the scale of the void around it. It cannot ask whether other galaxies know they exist. The fact that a temporary arrangement of carbon and water and electrical signals somewhere on the surface of an unremarkable rocky planet in an unremarkable spiral arm of a perfectly average galaxy is capable of asking these questions at all is itself one of the most remarkable things the universe contains. The James Webb Space Telescope cost $10 billion and 30 years of scientific labor. What it has produced is not comfort. It has produced precision, precise measurements of how wrong our models were, precise confirmation of anomalies that standard physics cannot explain, precise imagery of a universe far more complex and far less tidy than our theories predicted. What remains to be understood is vast. We do not know whether the early massive galaxies indicate a flaw in our model of galaxy formation, a longer cosmic history than we assumed, or an inherited structure from a previous cosmic epoch. We do not know whether the dark flow is caused by a concentration of mass outside our observable universe, a neighboring universe exerting gravitational influence, or something our physics has not yet been able to conceptualize. We do not know whether the Higgs field is truly metastable, and if so, how close to the boundary of stability its current value sits. We do not know whether the silence of the cosmos represents the rarity of life, the strategic caution of hidden civilizations, or something we have not yet thought to look for. We do not know whether the holographic principle is a mathematical curiosity or a description of the actual architecture of reality. We do not know whether the universe will end in a big rip, a heat death, a big bounce, or simply continue expanding forever until the last star flickers out in the cold dark. These are not gaps in the margin. These are gaps at the center. James Webb is not a telescope that provides answers. It is a telescope that generates better questions, more precisely specified questions, questions with enough resolution to begin ruling out wrong answers. The impossible galaxies of the early universe are not going away as we improve our data. They are becoming clearer and more numerous. The Hubble tension is not resolving. The dark flow signal is not dissipating. These anomalies are becoming harder to dismiss, not easier. What comes next is the work of reconciling a model with its contradictions. Cosmologists are currently developing extensions to the standard lambda-CDM model that incorporate new forms of dark energy, early dark energy, that would have affected the universe in its first moments. Interacting dark matter that exchanges force with ordinary matter in ways not previously accounted for, and modifications to the theory of general relativity that operate at cosmological scales, without disrupting the theory's extraordinary precision at smaller scales. New observatories are being designed specifically to address the questions James Webb has sharpened. The Nancy Grace Roman Space Telescope will map the distribution of dark energy across cosmic history with unprecedented statistical precision. The extremely large telescope, currently under construction in the Atacama Desert in Chile, will combine a mere 39 meters in diameter with instruments capable of detecting the atmospheric signatures of nearby exoplanets with a sensitivity James Webb cannot match. The next decade will determine whether the Hubble tension is a symptom of missing physics or an artifact of systematic error. It will determine whether the early massive galaxies can be explained by revising the timescale for star formation, or whether they require a genuinely new cosmological framework. It will determine whether any exoplanet atmosphere carries the distinctive chemical signature of industrial biology, the manufactured gases that nature does not produce. Any one of these outcomes would be significant. Some of them would be transformative in ways that are difficult to anticipate. What the telescope cannot do, what no instrument can do, is resolve the deeper philosophical weight of its own findings. The universe it reveals is not the universe we thought we lived in. It is older than we thought, or at least behaving as if it might be. It is more violent at its outer boundaries. It is less hospitable in its available real estate than our optimistic projections suggested, and it is built from physics that may not be as stable as we required. We built James Webb to see further than any human eye had ever seen. We pointed it at the beginning of time and asked what was there. The answer it has returned is not a simple one. It is a catalog of things we do not understand, packaged in precision measurements that rule out the comfortable explanations. The universe is not what we thought it was. It is larger, stranger, older in its behavior, more violent in its structure, and less hospitable in its chemistry than we believed. And we are only beginning to develop the questions sharp enough to find out why. The fact that we can ask is still, when you consider everything James Webb has shown us, the most remarkable thing of all. If you found this journey through the cosmos worthwhile, consider sharing it with someone who deserves to have their assumptions shaken. The universe is most interesting to the people who refuse to stop questioning it. Let us go back to the beginning of this story and trace it more carefully, because the surface-level summary does not capture how deeply the James Webb findings have fractured the assumptions that modern cosmology was built on. To understand what is truly broken, you need to understand what the standard model actually predicted, and why those predictions were considered so reliable. The lambda-CDM model, the lambda cold dark matter model, is the cosmological standard model that has governed our understanding of the universe's structure and history for the past several decades. Lambda refers to the cosmological constant, which is the mathematical term Einstein introduced to his equations of general relativity to describe what we now call dark energy, the mysterious energy of empty space that causes the universe's expansion to accelerate. CDM stands for cold dark matter, the hypothetical non-luminous matter that is thought to make up roughly 27% of the universe's total energy content. The model made specific, testable predictions. It predicted a specific rate of structure formation, the speed at which gravity would pull matter together into galaxies, clusters of galaxies, and the vast filamentary web of cosmic structure we observe today. It predicted that small structures would form first and merge over time into larger structures, a process called hierarchical structure formation. In this picture, the first objects to form after the cosmic dark ages would be small dwarf galaxies, which would then merge over billions of years to build the massive galaxies we see in the universe today. This is why JADES GSZ14 and galaxies like it are so destabilizing. They are not small. They are not primitive. They are the kind of massive, metal-enriched structures that the Lambda CDM model says should require billions of years of hierarchical assembly. Finding them at 290 million years after the Big Bang is not an anomaly within the model. It is a contradiction of one of the model's most basic predictions. The model made this prediction for a reason grounded in physics. Dark matter is cold, meaning its particles move slowly compared to the speed of light. This slowness is important because fast-moving particles tend to stream out of gravitational wells before they can accumulate into structures. Cold dark matter particles, moving slowly, should cluster together readily, forming the gravitational scaffolding that ordinary matter then fills in. The prediction was that dark matter halos would form first. Ordinary matter would then flow into those halos and cool and condense into stars, and galaxies would gradually build up from small beginnings over timescales of hundreds of millions to billions of years. The James Webb data is forcing a reevaluation of every step in this chain. Either dark matter is not behaving the way the model predicts, or ordinary matter can somehow assemble into massive structures independently of dark matter scaffolding, or the dark matter halos form faster than the model says they should, or some process was active in the early universe that efficiently compressed ordinary matter into dense structures at a rate far exceeding theoretical expectations. None of these alternatives is easy. Each one requires modifying or discarding assumptions that are supported by substantial independent evidence. Dark matter's existence, while not directly confirmed through the detection of its individual particles, is supported by galaxy rotation curves, gravitational lensing observations, and the structure of the cosmic microwave background in ways that are very difficult to explain without it. Abandoning cold dark matter would require replacing it with something that explains all of those observations equally well. The situation has driven some theorists to explore alternatives that would have been considered heretical a decade ago. Models involving warm dark matter, whose particles move faster and would cluster differently, have been revisited. Models involving early dark energy, a component of dark energy that was significant in the first moments after the Big Bang and then faded, have gained traction because they can modify the expansion rate in ways that affect structure formation timescales. Models involving primordial black holes that formed in the very early universe from density fluctuations rather than from stellar collapse, have been considered as potential seeds for rapid galaxy formation. Each of these alternatives solves part of the problem and creates other problems. This is the frustrating reality of a field whose foundational model is being challenged by data that its architects never anticipated. The cosmic microwave background, often abbreviated as the CMB, is the oldest light in the universe. It was emitted when the universe was approximately 380,000 years old, at the moment when the universe cooled enough for protons and electrons to combine into neutral hydrogen atoms, allowing photons to travel freely for the first time. Before that moment, the universe was an opaque plasma, and no light could propagate through it. The CMB is the afterglow of that transition, stretched by cosmic expansion from high-energy photons to microwave radiation, and it fills the entire sky uniformly in every direction. The CMB is cosmology's most precise instrument. Its tiny temperature fluctuations, variations of roughly 1 part in 100,000 across the sky, encode the initial conditions of the universe. By analyzing the pattern of these fluctuations, cosmologists can determine the geometry, composition, and early history of the universe with extraordinary precision. The lambda-CDM model was, in large part, constructed to fit the CMB data, and it does so with remarkable accuracy. This is what makes the Hubble tension so unsettling. The CMB gives one answer for the expansion rate of the universe. Direct observations of the current universe give a different answer. Both measurements are precise. Both are cross-checked by multiple independent methods. They simply disagree. When the tension first emerged in the data, the immediate assumption was that one set of measurements must be systematically wrong in some way that had not been identified. Perhaps there were errors in the calibration of the Cepheid variable stars used as distance markers. Perhaps the local universe contained unusual density fluctuations that made it unrepresentative of the universe as a whole. Perhaps there were subtle systematic errors in the CMB analysis. James Webb was expected by many to resolve the tension in favor of the CMB value. The hope was that by providing more precise measurements of Cepheid distances in a larger number of galaxies, James Webb would reveal that previous measurements of the local expansion rate were slightly biased toward higher values, and that the true value would turn out to be consistent with the CMB prediction. This did not happen. James Webb's measurements of Cepheid stars have been more precise than any previous measurement, and they have confirmed the higher local expansion rate. The tension has not resolved. It has been confirmed. The disagreement between the two methods is real, and it requires a physical explanation. The leading physical explanations fall into two categories. The first involves new physics in the early universe, some energy component or process that was active in the first few 100,000 years after the Big Bang, and that affected the expansion rate in ways not included in the standard model. Early dark energy is the leading candidate in this category. It would have caused the universe to expand slightly faster in its first moments, shifting the scale of the CMB fluctuations in ways that change the inferred expansion rate. The second category involves new physics in the late universe, modifications to dark energy or gravity that affect the current expansion rate without changing the early universe. Some modifications to general relativity that introduce additional degrees of freedom for gravity at cosmological scales fall into this category. Neither category provides a clean solution. Early dark energy models that resolve the Hubble tension tend to worsen the fit to other features of the CMB, creating a whack-a-mole problem where fixing one measurement breaks another. Late universe modifications face similar constraints from the precision of CMB measurements and large-scale structure surveys. No proposed solution has achieved consensus in the field. What James Webb has done is sharpen the problem to the point where it can no longer be ignored or hoped away. The telescope has turned a worrying discrepancy into a confirmed crisis. This is scientifically valuable, even if it is uncomfortable. A mystery that is precisely specified is a mystery that can eventually be solved. Let us talk about the specific physical mechanism by which James Webb performs its most remarkable kind of science: the detection of exoplanet atmospheres. When a planet passes in front of its host star from our perspective, a small fraction of the star's light is blocked by the planet's solid body. This is the transit signal, a brief, predictable dimming of starlight that repeats with each orbital period and allows us to detect planets and measure their sizes and orbital periods. This technique has been used by telescopes including the Kepler and TESS missions to discover thousands of exoplanets. But the transit is also a window. The planet's body is opaque, but its atmosphere is not. The atmosphere is a thin shell, and as the planet moves across the star's face, the very edge of the atmosphere, the limb, is briefly backlit. Starlight that would otherwise travel around the planet and miss us instead passes through this thin atmospheric shell at a glancing angle before continuing to our telescopes. As this light filters through the atmosphere, it interacts with the molecules present there. Molecules are not transparent to all wavelengths of light. Each type of molecule absorbs light at specific wavelengths determined by its chemical structure. Water vapor absorbs specific infrared wavelengths. Carbon dioxide absorbs others. Methane, ozone, and nitrous oxide each have their own distinctive absorption signatures. When the planet's atmosphere absorbs some wavelengths of the backlit starlight, the spectrum we receive shows dark bands at those wavelengths, like a barcode that encodes the chemical composition of the atmosphere. James Webb sensitivity to infrared wavelengths, the wavelengths at which most biologically and chemically interesting molecules absorb light, makes it uniquely capable of reading these atmospheric barcodes. Previous telescopes could detect broad atmospheric features in the spectra of large, close planets. James Webb can detect narrow absorption features in the spectra of smaller, more distant planets with a sensitivity that was previously impossible. The telescope has already produced the most detailed atmospheric spectrum ever obtained for an exoplanet, detecting water vapor, carbon dioxide, sulfur dioxide, and other molecules in the atmospheres of gas giant planets. It has detected the first unambiguous evidence of carbon-bearing molecules in the atmosphere of a super-Earth-class planet orbiting within the habitable zone of its star. These early results demonstrate the technique works. The question now is what it will find as it systematically surveys the growing catalog of known exoplanets. The Holy Grail is the atmospheric detection of oxygen coexisting with methane. On Earth, this combination is only maintained because life continuously replenishes both gases against their tendency to react with each other. In the absence of life, they would combine and both disappear within a geologically short period. Detecting both gases simultaneously in a planet's atmosphere would therefore be extremely strong evidence of biology. Not proof, because there might be exotic abiotic sources we have not anticipated, but evidence strong enough to require serious investigation. No such detection has been made yet. The atmospheres James Webb has studied in detail so far are of large planets that are unsuitable for life, as we understand it. Surveying smaller, rocky planets in the habitable zones of sun-like stars requires long observation times because their atmospheric signals are much weaker. The telescope is in the process of accumulating these observations. The field expects that within the current decade, James Webb will have surveyed enough habitable zone rocky planets to place meaningful statistical constraints on the prevalence of biosignatures. If those surveys return nothing, it will be one of the most significant negative results in the history of science. A null result from a survey of dozens of potentially habitable planets would strongly support the rare Earth hypothesis and suggest that Earth-like life is extraordinarily uncommon. If they return a positive detection, even a tentative one, it will change everything. The possibility of a detection is not pure fantasy. Recent research has identified a number of planets orbiting nearby stars that transit their hosts and are amenable to atmospheric characterization by James Webb. Among the most studied of these are the TRAPPIST-1 system, a group of 7 Earth-sized planets orbiting a red dwarf star roughly 40 light-years away, 3 of which are in the star's habitable zone. James Webb has already begun observing the atmospheres of the TRAPPIST-1 planets. So far, the results are mixed. Some show evidence of dense atmospheres. Others appear to have lost their atmospheres to the star's radiation. The habitable zone planets have not yet been observed with sufficient time to place strong constraints on their atmospheric composition. Whether TRAPPIST-1 or another system ultimately reveals the first biosignature is a question that will likely be answered in this decade. The implications of either answer, positive or negative, are equally profound. The broader question of consciousness in the universe, the question of whether minds exist only here or are scattered across the cosmos, is one that James Webb is now positioned to begin answering empirically rather than philosophically. For the entire history of human civilization, we have speculated about life elsewhere. Now, for the first time in history, We have a tool that can look at the chemical environment of distant worlds and read it directly. The universe has kept its own counsel on this question for 4 billion years of Earth's biological history. In the next 20 years, we may finally know whether it has been speaking elsewhere. There is a deeper dimension to the James Webb program that rarely receives the attention it deserves: the question of what the telescope is doing to our sense of cosmic scale. Every civilization in human history has had a cosmology, a story about the structure of the universe and our place within it. These stories have always been shaped by the observational tools available at the time. In an era before telescopes, the universe was the sphere of fixed stars visible to the naked eye, perhaps a few thousand light years in extent. The invention of the telescope expanded the known universe enormously, revealing galaxies beyond the Milky Way and demonstrating that the cosmos was far larger than any previous civilization had imagined. James Webb is doing to our understanding of the early universe what the first telescopes did to our understanding of its size. The telescope is revealing a past that is far more complex, far more active, and far more alien to our theoretical expectations than anyone predicted. The cosmology we will be working with in 50 years will likely differ from today's cosmology in ways that are, at this moment, difficult to anticipate. This is the nature of the scientific process, and it is worth being explicit about it. Science is not a catalog of fixed facts. It is a method for progressively reducing our uncertainty about reality by confronting our models with evidence. When the evidence contradicts the model changes. The models that survive are the ones that make predictions that are confirmed by subsequent evidence. The models that are discarded are the ones that fail this test. The Lambda CDM model is currently failing several tests. It will either be modified to accommodate the new data, or it will be replaced by a successor model that explains not only what the original model explained, but also what it got wrong. Either outcome represents progress. The anomalies are not a failure. They are the engine of discovery. James Webb is currently in the middle of its designed scientific lifetime. It launched in December of 2021 and is expected to operate for at least 20 years, with the possibility of longer depending on the depletion rate of its fuel. It is observing in 6 primary science areas: the physics of the early universe and first light, the growth of galaxies over cosmic time, the life cycle of stars from formation to death, the nature of planetary systems including our own solar system, and the characterization of exoplanet atmospheres. In each of these areas, the telescope has already made discoveries that are rewriting textbooks. In the area of early galaxy formation, the impossible early galaxies are the headline result. But beneath that headline, there are hundreds of individual objects that each represent new physics or new constraints on existing models. In the area of stellar physics, James Webb has for the first time directly imaged the environments around forming stars with the clarity to see the circumstellar disks from which planetary systems emerge. In the area of planetary science, it has detected the composition of the atmospheres of solar system bodies with new precision, and has begun the systematic program of exoplanet atmospheric characterization. The data is being released publicly and continuously. Teams of astronomers around the world are analyzing the telescope's observations, submitting their findings to preprint servers before formal peer review, and engaging in a scientific conversation that is faster and more internationally collaborative than at any previous point in history. The discoveries are not coming from a single team or a single institution. They are emerging simultaneously from dozens of research groups, approaching the same data from different theoretical perspectives. This distributed, rapid, globally collaborative approach to interpreting an unprecedented dataset is itself new. It means that the scientific community's understanding of what James Webb is revealing evolves quickly. Findings that seem firm one month are sometimes revised the next as new analysis techniques or new comparison data are applied. The impossible early galaxies, for example, were initially flagged as candidate objects before their distances were confirmed spectroscopically. The confirmation of their distances through spectroscopic redshift measurements took additional observing time and careful analysis. This process of progressive confirmation is how modern astronomy works, and James Webb is operating within it at a pace and scale that the community has not previously experienced. The volume of data from James Webb is not just scientifically rich, it is logistically challenging to analyze and interpret, and it is producing a literature of results that no single scientist can keep pace with. What this means for the long-term scientific impact of the telescope is that we are still in the early stages of understanding what it has revealed. The results published in the first 3 years of operation are almost certainly not the most significant results the telescope will produce. As analysis techniques improve, as new theoretical frameworks are developed in response to the data, and as the telescope's survey programs accumulate more statistics, the picture it provides will become clearer, more precise, and likely more surprising. The universe has a way of being more interesting than our theories predict. James Webb, more than any instrument in the history of astronomy, is making that principle concrete and quantifiable. We began with a simple, clarifying observation. We built a $10 billion machine to look at the beginning of the universe, and the beginning of the universe looked wrong. The galaxies were too big too fast. The chemistry was too evolved too early. The dark ages were not dark. The timeline we had trusted for half a century did not survive contact with the data. What we have traced since then is the full consequence of that initial rupture. The crisis in galaxy formation theory leads to questions about the age and history of the universe. Those questions open into the possibility of previous cosmic cycles, of inherited structures, of a universe that is not new but ancient in ways our clocks were not designed to measure. The boundaries of our observable region reveal forces acting from outside them, and the cold bruise in the microwave background suggests we have already been touched by whatever exists beyond our visible horizon. The silence of the cosmos, confirmed now not just by the absence of radio signals, but by the chemical barrenness of planet after planet, raises the possibility that we are not one of many but one of very few, or perhaps one of one. And the physics of the stage itself, from the Hubble tension to the metastability of the Higgs field, from the holographic structure of black holes to the pixel-like resolution of spacetime at the Planck scale, suggests that the reality we inhabit is not the solid, reliable, permanent structure we assumed. None of this, not a single discovery in this entire catalog of disruption, has reduced the scientific community's commitment to understanding it more precisely. Quite the opposite. The James Webb Telescope was approved, funded, built, launched, and deployed precisely because the community understood that the questions at the frontier of cosmology required better data. The telescope is now providing that data, and the questions it is answering are generating better questions, which will drive the next generation of instruments and the next generation of physicists. The universe is not trying to be understood. It simply is. We are the part of it that insists on understanding anyway, the local, temporary, improbable arrangement of matter that turned the cosmos's own atoms into eyes and aimed those eyes at the stars. James Webb is the best pair of eyes we have ever built, and what those eyes are telling us is that the universe is older and stranger and more violent and more alive with unanswered questions than we knew. That this should feel like a beginning rather than an ending is perhaps the most important thing to take away from all of it. We are at the start of something. We do not yet know what it is, but we have, for the first time, instruments good enough to find out. There is one more dimension of the James Webb discoveries that deserves careful attention, and it concerns not the universe outside us but the nature of our perception of it. We have been talking about the telescope as if it is a neutral, transparent instrument that simply shows us what is there, But the telescope sees only light, and light is not the present. It is the past. Every observation James Webb makes is an observation of something that no longer exists in the state it appears. The light from JADES GS-Z14, the galaxy at the edge of cosmic time, left its source roughly 13.5 billion years ago. The galaxy that emitted that light has had 13.5 billion years to evolve, merge with other galaxies, lose its gas supply, run out of new stars, and either transform into something unrecognizable or cease to exist as a distinct object altogether. What James Webb is seeing is a fossil, a preserved image of something that was true at a specific moment in the distant past. This is true of everything the telescope sees. The most nearby galaxies in its field of view are millions of light years away, meaning we see them as they were millions of years ago. The most distant objects are billions of light years away, and we see them across billions of years of elapsed time. When the telescope takes a deep field image, an image of a single patch of sky too small to cover the face of the moon, it is simultaneously looking across billions of light years of space and billions of years of time. The most distant galaxies in that image are being seen in their infancy, while their nearby neighbors are being seen as mature, evolved structures. What this means is that the telescope does not see the universe. It sees a slice through the universe's history, a cross-section that combines objects at many different evolutionary states into a single image. The challenge of cosmology is to take this jumbled cross-section and reconstruct from it a coherent history. To understand how the objects at different distances and different ages are related to each other, how the galaxies of the early universe evolved into the galaxies of the present, and how the physics governing them changed or remained the same across the expanse of cosmic time. The impossible early galaxies make this reconstruction difficult because they do not fit neatly into the evolutionary sequence. If the small, primitive early galaxies predicted by hierarchical structure formation do not appear in James Webb data in the expected numbers, and if large, mature galaxies appear much earlier than expected, the chain of cosmic evolution we thought we understood is broken. We cannot simply say the early universe contained small galaxies that grew into large ones, if the large ones were already there when the small ones should have been just forming. The work of reconstructing a consistent cosmic history from the James Webb data is ongoing. It involves not just observation but extensive theoretical modeling, numerical simulations of galaxy formation and evolution run on supercomputers, statistical analysis of large catalogs of galaxies at different redshifts, and comparison with observations from other telescopes operating at different wavelengths. Radio telescopes, for example, can detect the neutral hydrogen gas that is the raw material for star formation in galaxies at all cosmic epochs. X-ray telescopes can detect the hot gas that fills clusters of galaxies and trace the growth of large-scale structure. Infrared telescopes on the ground can reach wavelengths that James Webb does not cover. The combination of these different observational windows on the universe provides a more complete picture than any single instrument alone. James Webb sits at the center of this multi-wavelength effort as the instrument with the greatest sensitivity to the faint, distant objects that define the frontier of our knowledge. When James Webb identifies an unusual or important object, other telescopes can observe it at wavelengths James Webb cannot access. The result is a collaborative, multi-instrument portrait of the universe that no single telescope could produce alone. The scientific collaborations that use James Webb data are international. The telescope was built by NASA in partnership with the European Space Agency and the Canadian Space Agency. Astronomers from dozens of countries use its data. The results it produces are shared openly and analyzed by a global community. The impossible galaxies of the early universe were not discovered by one team. They were identified, characterized, confirmed, and placed in context by dozens of teams working simultaneously and cross-checking each other's results. This global, open collaboration is one of the underappreciated achievements of modern astronomy. The scale of the scientific questions being addressed requires the pooled expertise and resources of the entire international community. No single country or institution could build James Webb. No single team could fully analyze its data. The telescope is a product of humanity's collective capacity for sustained, coordinated, long-term scientific effort. In a world that often emphasizes division and competition, the James Webb Space Telescope is a reminder of what becomes possible when that impulse is redirected toward a shared goal. There is something worth sitting with in the particular kind of discomfort that the James Webb discoveries produce. It is not the discomfort of bad news about the world in any immediate, personal sense. The impossible galaxies pose no threat to our daily lives. The Hubble tension will not cause any practical disruption regardless of how it is resolved. Vacuum decay, though theoretically possible, is not something any rational person can plan around or protect themselves from. The discomfort is of a different kind. It is the discomfort of discovering that the map we have been using to navigate our understanding of reality is wrong in ways we did not know it was wrong. We thought we understood the early universe. We thought we knew when the first stars lit up and roughly how long it took for galaxies to form. We thought the Hubble constant was settled. We thought the stability of the vacuum was something we did not need to worry about in a practical sense, not because it is safe, but because there is nothing anyone could do about it, and the probability of a local nucleation event in any given human lifetime is negligible. What James Webb has done is reveal that our confidence was not fully earned. The model we trusted was more provisional than we realized. The data we did not yet have access to, the deep infrared observations of the earliest epochs of cosmic history, turned out to contain surprises that our theories did not predict. This is uncomfortable because we are pattern-seeking creatures who rely on models to navigate a complex world. When a model fails, it creates cognitive dissonance. We have to hold two things simultaneously: the recognition that the model was wrong in specific ways, and the continued need to use models at all, because we have no alternative. The response to a broken model is not to abandon modeling. It is to build a better model. The James Webb discoveries are demanding a better model of cosmic history. The field is working to supply one. The process is not fast, because the right model has to account not just for the James Webb anomalies, but for everything the previous model correctly predicted. You cannot throw out a framework that explains thousands of observations just because it fails on a handful of new ones. You have to find the framework that explains all of them simultaneously. This is the hardest kind of science. It requires intellectual flexibility combined with rigorous quantitative constraint. It requires the willingness to consider radical alternatives while maintaining high standards of evidence. It requires the patience to sit with uncertainty while the observations accumulate and the theory develops. The physicists and astronomers working on these questions are doing exactly that. They are not panicking. They are not abandoning the field. They are asking more precise questions, building better instruments, developing more sophisticated theoretical tools, and refining their understanding one measurement at a time. The universe is not hostile to being understood. It is simply under no obligation to be simple. James Webb has revealed that it is not simple in specific, measurable, replicable ways, and that is precisely what makes it tractable. A universe that was simply mysterious would be one we could never understand. A universe that is mysterious in specific, quantifiable ways is one that we can, eventually, decode. The $10 billion and 30 years of effort that produced James Webb bought humanity the most precise view of cosmic history ever achieved. What that view revealed is that we have more to learn than we thought. Given the nature of the universe, this should not be surprising. What is surprising is the precision with which James Webb has revealed what we do not yet know. That precision is the beginning of the next chapter of cosmology, not the end of understanding, but the beginning of understanding more completely. The telescope continues to observe, the data continues to arrive, and the universe, indifferent to our theories and our timelines, continues to be exactly what it is. We are fortunate, in the particular way that temporary, curious, self-aware arrangements of matter can be fortunate, to be alive in the era when the seeing became this good. Let us now look more carefully at what the James Webb Telescope has revealed about something closer to home, the birth and death of stars. Because the impossible early galaxies are not just about the age of structures. They are about the rate at which stars formed, burned, and died in the early universe, and the implications of that rate are startling. Stars are not just points of light. They are the universe's chemistry laboratories. Every atom heavier than helium in the known universe was either created in the core of a star through nuclear fusion or in the catastrophic explosion of a dying star, a supernova. The carbon in your body was forged in the interior of a star that died before the sun was born. The oxygen in the air you are breathing was produced by a star and scattered into the galaxy billions of years ago. The iron in your blood was created in the collapsing core of a massive star at the moment of its death. You are made of stardust in a literal and precise sense that is not metaphorical. For a galaxy to contain oxygen and carbon-bearing molecules at 290 million years after the Big Bang, as JADES GSZ14 does, stars must have formed, run through their entire life cycles, exploded, and scattered their nucleosynthetic products into the interstellar medium at a rate far exceeding what the standard model of star formation predicts. A massive star, the kind that produces the heaviest elements and dies as a supernova, lives for only a few million years before exploding. But even a few million years of stellar evolution requires stars to have begun forming sufficiently early for multiple generations to have completed their cycles by the time the galaxy is observed. Working backward from the chemical signatures James Webb detects, astronomers can estimate how many generations of stars must have preceded the observed galaxy. The answer is typically more than the available time accommodates, given the standard model's predictions for when star formation could have commenced. Something in the early universe was forming stars faster, or stars were beginning to form earlier than the theory allows. One possibility being investigated is that the initial mass function, the distribution of masses among newly formed stars, was different in the early universe than it is today. In the present-day universe, when gas clouds collapse to form stars, they produce a mixture of stellar masses following a specific pattern, with many low-mass stars and fewer high-mass stars. Low-mass stars burn slowly and live for tens of billions of years. High-mass stars burn furiously and die within millions of years, producing much larger quantities of heavy elements per unit of stellar mass. If the early universe preferentially formed more massive stars, the chemical enrichment of galaxies would have proceeded much faster than the current initial mass function would predict. There is theoretical reason to think this might have been the case. The gas in the early universe was composed almost entirely of hydrogen and helium, with essentially no heavy elements. The cooling of gas clouds through heavy element emission lines, which is an important step in the collapse of gas into stars in the present-day universe, would have been less efficient in the metal-free early universe. Simulations of primordial star formation suggest that the first generation of stars, known as population 3 stars, may have been extremely massive, hundreds of times the mass of the Sun. These stars would have burned briefly and brilliantly, producing enormous quantities of heavy elements in their short lives before exploding as supernovae or collapsing directly into black holes. James Webb is specifically designed to search for population 3 stars. These stars would emit light at characteristic wavelengths that should be detectable by the telescope in the spectra of very high redshift galaxies. No unambiguous detection of population 3 stars has been made yet, but the telescope has found candidate objects in several high redshift galaxies whose spectra show features consistent with the presence of extremely massive, metal-free stars. These candidates are being observed with additional telescope time to confirm or rule out the population 3 interpretation. If population 3 stars were indeed extremely massive and formed rapidly in the early universe, they would help explain both the rapid chemical enrichment seen in early galaxies and the existence of massive black holes at very high redshifts. Massive population 3 stars would collapse at the end of their short lives to produce black holes of considerable mass, which could then grow rapidly by accreting surrounding gas and merging with other black holes to produce the supermassive black holes observed at the centers of galaxies even in the early universe. The supermassive black holes at the centers of early galaxies are themselves a significant puzzle. These objects, with masses ranging from hundreds of millions to billions of times the mass of the Sun, are observed in galaxies at redshifts greater than 6, meaning they existed when the universe was less than 1 billion years old. Growing a black hole to this mass in less than 1 billion years requires either extremely rapid accretion of surrounding material, a massive seed black hole to start with, or a combination of both. The standard pathways for black hole formation, through the collapse of massive stars, produce initial black holes of tens to hundreds of solar masses at most. Growing these seeds by accretion to billions of solar masses in less than 1 billion years requires sustained near-maximum accretion rates that are difficult to achieve physically. James Webb is studying high-redshift quasars, the brilliantly luminous active galactic nuclei powered by rapidly accreting supermassive black holes, to understand how their central black holes grew so massive so quickly. The telescope's infrared sensitivity allows it to observe these objects at redshifts that were previously inaccessible, and its spectroscopic capabilities allow it to measure the masses of the black holes through the dynamics of the gas and stars surrounding them. The results are consistently surprising. The supermassive black holes in high redshift quasars are often much more massive relative to the galaxies hosting them than is typical in the present-day universe. In nearby galaxies, there is a tight relationship between the mass of the central black hole and the mass of the galaxy's central bulge. The black hole is typically about 0.1% of the bulge mass. But in high redshift galaxies, James Webb is finding black holes that are disproportionately large relative to their host galaxies, suggesting that black hole growth preceded galaxy growth in the early universe rather than proceeding in lockstep. This inversion of the expected relationship between black hole and galaxy growth is another piece of the growing picture of an early universe that was more dynamically active and more rapidly evolving than our theoretical framework predicted. The standard model assumed a degree of regulated coevolution between central black holes and their host galaxies, mediated by feedback processes in which the energy released by accreting black holes heats and expels the surrounding gas, regulating both the star formation rate and the black hole's own growth. The James Webb data suggests this regulated coevolution was not operating in the same way in the earliest galaxies, or that it was operating on different timescales than the model assumed. Understanding the relationship between supermassive black holes and the galaxies they inhabit across cosmic time is one of the central scientific programs of the James Webb mission. The telescope is accumulating a statistical sample of galaxies and their central black holes at progressively higher redshifts, building the empirical database needed to trace the coevolution of black holes and galaxies from the present day back to the earliest epochs observable with current technology. The picture emerging from this program is of an early universe that was wild and creative in ways that the orderly, well-regulated present-day universe is not. Today's universe is, cosmologically speaking, old and quiet. The rate of star formation across the universe peaked roughly 10 billion years ago and has been declining since. The most active, most luminous, most rapidly evolving galaxies in the universe were the ones that existed in the early universe, and James Webb is giving us our first clear view of those objects in their prime. What the telescope is revealing is that we live in the universe's retirement. The spectacular fireworks of the early cosmic era, the rapid galaxy formation, the violently accreting quasars, the explosive enrichment of the interstellar medium with heavy elements, have given way to the quieter, slower processes of an aging cosmos. Our sun is a middle-aged star in a middle-aged galaxy in a universe that has passed its period of greatest activity. The dramatic events that shape the large-scale structure around us, the formation of the Milky Way, the assembly of our local cluster of galaxies, the seeding of the interstellar medium with the heavy elements that make up our planet and our bodies, all of this was accomplished in the energetic youth of a universe that is now in the process of winding down. This perspective is both humbling and clarifying. We are not at the beginning of the story. We are near the end of the universe's most active phase, living in the long, quiet era that follows the tumultuous period of creation. The universe around us is the residue of events that happened long ago. The elements in our bodies, the structure of our galaxy, the positions of the stars visible in our night sky, all of this is the settled outcome of processes that were complete billions of years before the Earth formed. James Webb is allowing us, for the first time, to see those earlier processes directly, to observe the universe as it was during the period of its greatest activity, to compare the wild youth of the cosmos with the settled maturity of the universe we inhabit. The comparison is both scientifically invaluable and philosophically significant. We are products of the universe's past. Everything that makes us possible, every atom in our bodies, every stable orbit in our solar system, every convenient property of the physical constants that allows chemistry and biology to exist, is a consequence of processes that unfolded in the first few billion years of cosmic history. The universe made us, not by intention, but by the relentless operation of physical law across time. And now, we are using the intelligence that arose from those processes to look back at the processes themselves, to understand the history of our own making. This is the deepest loop in the story of the James Webb Telescope. It is not just a machine looking at the past. It is a product of the universe looking at its own history. The atoms in the telescope's mirrors were forged in dying stars billions of years ago. The scientists who designed it are made of atoms with an equally ancient provenance. The fundamental physical laws that the telescope is testing were operating long before any mind existed to formulate them as equations. The universe does not know it is being observed. It does not know that a small, temporary arrangement of its own matter has built instruments sophisticated enough to read its history. But we know, and the knowledge that we can do this, that we have done this, that we are doing this right now, is perhaps the most remarkable fact that the James Webb Space Telescope has confirmed. Not just what the universe contains, but that we can see it. There is a final thread worth pulling on before we close. The specific question of what the James Webb Telescope means for the concept of cosmic loneliness. For most of human history, the question of whether we are alone in the universe was purely philosophical. We had no means of investigating it empirically. We could speculate, debate, and construct arguments from first principles, but we could not look. The development of radio astronomy in the 20th century gave us the first tool to search for technological signals from other civilizations, but the absence of a detected signal is ambiguous. It could mean no one is there, or it could mean they are not broadcasting on radio frequencies, or it could mean the universe is simply too large for signals to have reached us yet. James Webb changes the nature of the question. For the first time, we have a tool that can detect the chemical byproducts of biology and technology in the atmospheres of planets we will never visit. The search for extraterrestrial intelligence has, for decades, been a search for intentional signals. James Webb turns it into a search for unintentional evidence. You cannot hide your chemistry the way you can hide a radio transmitter. If life exists on a planet with an observable atmosphere, James Webb may eventually detect it whether that life intends to be found or not. The significance of this shift cannot be overstated. If James Webb surveys dozens of potentially habitable exoplanets over the next decade and finds no atmospheric evidence of life, we will have, for the first time, empirical evidence favoring the hypothesis that life is rare. Not proof, because the sample is small and the negative result is ambiguous, but the most direct observational test of the rare Earth hypothesis ever conducted. If it finds evidence of life, even tentative evidence, the implications for our understanding of our place in the universe will be immediate and irreversible. We are living through the years immediately preceding what may be the most significant discovery in the history of science, or we are living through the years that will confirm, with unprecedented observational precision, that we are alone. Both possibilities are extraordinary. The universe is not ambiguous about which it would prefer, because the universe has no preferences. We are the ones with preferences, and the tension of not knowing is entirely ours to hold. The James Webb Space Telescope launched on December 25th of 2021, on a trajectory toward a point in space called the second Lagrange point, located approximately 1.5 million kilometers from Earth in the direction away from the Sun. At this gravitational balance point, the telescope orbits the Sun in synchrony with the Earth, always keeping the Earth and Sun on the same side, allowing the large sunshield to keep the telescope cold enough to detect the faint infrared radiation from the most distant galaxies. The first full-color images and spectroscopic data were released to the public in July of 2022, and in the years since, the telescope has fundamentally changed the field of observational cosmology. The results already published represent only a fraction of the observations the telescope will eventually produce. The science programs that have been approved for the first years of the mission cover a fraction of the scientific questions the telescope is capable of addressing. As the telescope continues to observe, and the archive of data continues to grow, the understanding we build from it will become progressively deeper and more comprehensive. The anomalies identified in the first years of operation will either be resolved by subsequent observations that provide more context and precision, or they will be confirmed as genuine features of the universe that require fundamental revisions to our theories. The history of astronomy suggests that the latter is more likely. Every time humanity has built a significantly more powerful telescope, the universe has revealed something unexpected. The Hubble Space Telescope showed us that the expansion of the universe is accelerating, a discovery that earned the Nobel Prize and introduced dark energy as a new component of cosmic reality. The cosmic microwave background experiments showed us the precise acoustic signature of the early universe and provided the observational foundation for the standard cosmological model. Ground-based surveys of millions of galaxies revealed the three-dimensional large-scale structure of the cosmos in detail that transformed our understanding of how galaxies are distributed in space. James Webb is the next step in this progression, and consistent with the pattern, it is showing us things we did not expect. The impossible early galaxies, the confirmed Hubble tension, the chemical signatures of mature stellar populations in the young universe, the disproportionately massive black holes in the first galaxies, the barren, chemically stable atmospheres of planet after planet. These are not random anomalies. They are converging lines of evidence pointing towards something our current framework is missing. Finding out what that something is will be the work of the next generation of physicists and astronomers. Some of them are in graduate school right now, studying the James Webb data, building the theoretical tools to interpret it, and designing the successor instruments that will extend its reach further in time and depth. Some of them have not yet been born. The universe has been around for 13.8 billion years, give or take the uncertainty introduced by the Hubble tension. Humanity has been asking serious questions about it for perhaps 10,000 years, and conducting rigorous quantitative science about it for perhaps 400 years. The James Webb Telescope represents 400 years of accumulated understanding, applied to the most precise observational program in history. And what it has found is that we have more to learn. This is not a failure. It is the most honest and exciting thing that science can produce, a precise, quantified, observationally grounded statement of our ignorance. We know what we do not know with greater precision than ever before. That is the beginning of knowing. The telescope will continue to observe. The data will continue to reveal. The universe will continue to be, as it has always been, stranger and larger and older and more intricate than we imagined. And we will continue to look. That is what we do. That is what we are. If this exploration of what the universe is revealing to us has left you with more questions than answers, that is exactly the right response. Subscribe and stay with the conversation, because the questions only get better.